In this example, we would like to evaluate this given definite integral. And then on this example, we can see, so on this definite integral, on the lower limit of integration, we have given 0. At the upper limit of integration, we have given 1. And then on the integrand, we have given 7 times cosine function composed with pi t divided by 2, right? So that's what we have. So since this is definite integral, and then this function over here 7 times cosine of pi t over 2, that function is continuous on 0 to 1 on that closed interval, so we can definitely use the fundamental theorem of calculus. So if we want to use the fundamental theorem of calculus, we need to know what is the antiderivative of this one, right? Particular antiderivative of this, so that we can use the fundamental theorem of calculus. So that's what the strategy we want to use. But to find the entire derivative of this integrand over here, this function over here, we can see that this cosine function is composed with pi t divided by 2. So there is no like the immediate formula that we want to use, but what we can do is we can use the substitution rule here to first figure out the entire derivative. But since we also want to use the fundamental theorem of calculus, so let's try to use the substitution, and then also try to change this limit of integration too, because the limit of integration currently is value, these values are given for t equal to 0, t equal to 1, right? So if you want to use the substitution, I want to change that also in terms of some other variable. So let's try that. So let's suppose here u is the cosine function composed with pi t divided by 2. So I just want to suppose that is actually u. So if I suppose in that way, I can actually compute the differential du, which is the derivative of pi t divided by 2 times differential dt, right? So what is the derivative of pi t divided by 2? Pi over 2 is a constant multiplied by t, right? So we can apply the constant multiple rule. So because of that, we'll have pi over 2 the constant as it is, multiplied by the derivative of the t with respect to t, but which is just 1. So pi over 2 is the derivative of that given function multiplied by differential dt. So that should be our differential du. So that's what we have. But not only these two, I actually want to also change this limit of integration over here, everything in terms of u. Okay, so currently these are value of t. I want to change that also in terms of u. So if I want to do that, here's what I can do. So since we have a relationship between the t and u over here, so let's use that relationship and then try to see when, let's say, the value of the t is 0, right? And then plug that in over here. When t is 0, what do we get for u? So when t is 0, so everything over here is 0, right? So we get u is 0. So when t is 0, the value of the u is 0. So that's what we get, right? In the same way, so over here we have 1 at the upper limit of integration, that is currently the value of t. So when t equal to 1, again that information, plug that in over here. So when you do that, we can solve for u, and then we get the value of the u is pi over 2 times t is 1, so just we get pi over 2. So that's how we can convert everything in terms of u. So now we have, suppose here, let's review here whatever we have done so far. So we have actually suppose now pi over t, pi times t over 2 is actually u. With the help of that, we compute the differential du, and not only that, since u is pi times t over 2, so with the help of that, when t is 0, we try to plug that information in over here and then get the value of u. And then when t is 1, we again plug that in over here and then get the value of the u. So we change kind of everything in terms of u. So when you do that, now we can actually change this given integral in terms of u, and then I hope that that is much more simpler than the current one. So now over here, this is the integral sign. At the lower limit of integration, that is 0, we have when t equal to 0, u will be 0. So we can write that down is 0, right? When t equal to 1, we have solved and we give the value of the u is pi half. So instead of that, we can change the, instead of 1, now we can change that into pi half, right? Now when we do that, let's try to work with the integrand over here. So that 7 is a constant, so let's keep that as it is, right? So let's write that down. And then after that, we have this cosine function composed with pi t over 2, and then pi t over 2 is u. So if that is the case, instead of this function over here, we can actually write down cosine of pi t over 2 is just u. That's what we have supposed here, right? So we can just write it down. So if that is the case, what is left over is just that differential dt. So what can we do for that? So over here you can see recently we have computed the differential du. On this relationship we do see that differential dt, right? So why don't you actually from this equation just solve for this dt? So from this a relation or the equation, let's say if we solve for dt, we get actually, if you solve for dt, how can we isolate dt? We need to multiply both side by, let's say, the reciprocal of pi over 2, which is 2 over pi. When we do that, we'll have dt is 2 over pi times differential du, and that's exactly we can actually replace back over here instead of dt. So let's instead of that dt, let's write down 2 over pi times du. All right, so we convert our given integral in as a function of u, everything now in terms of u, right? But let's try to see if we have simpler integral than the given one. So let's like the colleague, the let's say the what was that, the multiply the constants over here. So we have 7 times 2 over pi, which if you combine them, right, so you would get 7 times 2 is 14. So we will have 14 over pi, so we could write that down. And then after that we have the integral sign over here, 0 to pi half as it is. Then what is left over here is cosine of u du. That's the only thing left over. And then I think it is much more simpler because we just need to find the antiderivative of cosine u with respect to u. And then I believe we know that one, right? So what is the antiderivative of cosine of u? Sine of u, right? So okay, so then if that is the case, we can use now the fundamental theorem of calculus. So 14 over pi is just the constant, leave that as it is. And then antiderivative of cosine u is sine of u. So this is one of the particular antiderivative. So if you want to evaluate the definite integral and want to apply the fundamental theorem of calculus, this antiderivative need to be evaluated at the upper limit of integration, which is pi half, right? So that's what given over here. And then we need to evaluate this antiderivative at the lower limit of integration, which is currently given here as 0, and just find the difference between that. So let's do that then. So 14 over pi, evaluate this antiderivative at pi half, then we get what is that one, sine of pi half, right? And then evaluate this antiderivative at the lower limit of integration, which is sine of 0, and just find the difference between these two. So when we do that, now what do we get here? So sine of u, so sine function when you evaluate at 0, it is actually 0, right? And then sine of pi half, if you look into the unit circle chart, or let's say use the calculator, and if you are using the calculator, don't forget to keep it in the radian mode so that you can evaluate the trigonometric function correctly, right? So then we have sine of pi half, I think you'll get 1. So 1 minus 0 is 1. So if that is the case, 14 over pi, this is the value of the definite integral that we needed to evaluate.